Hello, my name is Mikhailo Trusov, and I work in Berezin Kharkiv National University. The topic of our current presentation is evaluation of Resemblyzer ability to authenticate the person by short audio records. Let's start. A wide range of portable and connected devices such as mobile phones, laptops, e-readers, smartwatches, wireless earbuds, robotic vacuum cleaners, and many others has become ubiquitous in modern life. This list could be extended considerably. However, it is indisputable fact that the Internet of Things has already become an integral component of contemporary society and that robots, in the broad sense of term, now serve as indispensable assistants in our daily activities. In this context, an important arises: how can users effectively interact with such assistants? One of the approaches involves the use of control interfaces, which may range from keyboards and touch panels to specialized devices capable of transmitting commands via radio frequency or infrared channels, as well as through voice-based commands. Among these, interaction via voice commands represents the most natural and straightforward way for issuing instructions, requesting actions, or retrieving information. In addition, this modality does not require specific skills or additional efforts associated with the utilization of specific input devices, and it typically offers the fastest way of communication. However, voice-based interaction is accompanied by a range of technical and practical challenges. For instance, background noise can significantly decrease voice recognition accuracy, while variations in dialects, speech rate, pronunciation, and accents further complicate reliable interpretation. More critically, voice control systems raise substantial privacy and security concerns. Beyond the inherent risks that speaking aloud may inadvertently disclose sensitive information, for example, passwords, PIN codes, or message content. It becomes critically important in contexts involving more sensitive systems than a coffee machine were issuing commands to mobile devices and industrial robot or even a combat drone. It is essential to ensure that the system can reliably authenticate the speaker and respond exclusively to authorized individuals. In the present work, we evaluated the potential of publicly available Python library Resemblyzer for user authentication based on short voice commands. Specifically, the main goal was to determine empirically the minimal audio conditions under which short voice commands can be used for robust user authentication with Resemblyzer. We focus on Resemblyzer library as the core speaker embedding tool due to its strong performance in voice print related tasks, public availability, and active maintaining by the community. Um, Compatibility with Python scientific ecosystem, and ability to operate in both batch and near real-time contexts. It leverages a pre-trained model based on the generalized end-to-end architecture, which was introduced by Google for speaker verification, enabling it to generate compact 256-dimensional speaker embeddings that generalize well even for short utterances. Once the embedding is computed, only the small vector, about 1 kilobyte, needs to be stored or compared, not the full audio. The pre-trained models is stored as a PyTorch file and can be located locally. It is reasonably small, from 15 to 20 megabytes, depending on the version. The size of model is significantly lighter than transformer-based model like Whisper, uh, a kappa, TDNN, or others. As can be seen from this table, Resemblyzer model is the smallest one. This advantage plays an important role, taking into consideration that it should be used in resource-constrained devices. Moreover, authentication based on voice print analysis in Resemblyzer library works purely on device with no need to send audio to cloud services. In other words, no network communication is required. The implementation of the work involves a set of tests with short audio records designed to emulate voice commands for a combat drone. All audio records were saved in a WAV format and produced with a standard computer microphone by sound recorder application, which is available at any Windows operating system. We deliberately avoided high-quality devices with the purpose to simulate the real-life conditions. Two types of voices, male and female, were included into the experiments. Information about audio records used and identification of the corresponding input sets are summarized in the slides. So you can see here the voicemail data set, the female data set, and also here you can see dataset which includes longer audio records used in our last experiment. For each audio recording, a voice print was generated using the Resemblyzer library, producing a 256 element array of floating values. Each array was saved in a separate CSV file named identically to its corresponding original audio file. The authentication process and evaluation of similarity between two voice prints can be quantified using cosine similarity, a widely used metric in speaker verification systems. Cosine similarity yields a value between -1 and +1, indicating how closely two voice print vectors align in the embedding space. Specifically, +1 value means almost identical voices. 0 indicates no similarity, and -1 value represents complete opposition, an outcome unlikely in the context of our work. Heuristic or empirical result equal or greater than 0.75 means successful authentication. In speaker verification system using cosine similarity, typical same speaker scores fall around 0.8 and 0.95. Different speaker scores often fall around 0.3 and 0.6. So, 0.75 is commonly used as a default threshold in prototyping or academic examples. In our first experiment, we compare voice prints received from dataset 1 between each other. The algorithm was the following. First, we selection of first CSV with voice print from the target folder. Second, comparison of this voice print with those voice prints stored in all other CSV files in the same target folder. Then record the calculated similarity scores in the results CSV file as a new row. Next, repetition of the process for the next CSV file with voice prints. The result of comparison for dataset 1 are summarized in the table. Given that all audio recordings were produced by the same speaker, we expect that all similarity scores would exceed 0.8. However, the result revealed numerous cases with values below this threshold, and in some instances even below 0.6. In the context of our uh, experiment, scores below 0.6 can be considered false negatives. The range between 0.6 and 0.8 represent an uncertain or threshold zone, and values above 0.8 indicate a successful match. To better understand the distribution of results, we calculated the proportional scores falling within each range. Resultant score is as follows. As you can see, only 30% of cases were successful, in spite of the expectation to have value close to 100%. Uh, we've done similar experiment with dataset related to audio records recorded by female. So it's a dataset 3. The result for this dataset were found to be notably better than those for previous dataset. We have 0 failed cases and threshold range less than half the size of the successful matches. To understand the factors contributing to this improvement at the next step of the study, we compared audio recording from the two datasets and tried to identify the characteristics that lead to the highest similarity score. The first step involved the detection of the cases with the largest differences between the two resulting similarity metrics. We take the similarity matrix from dataset 3 since it demonstrates the superior performance and subtract the corresponding matrix from dataset 1. In this context, the resulting delta serves as a quality indicator for the comparison. By summing the values in each column, we obtain a cumulative weight for the corresponding file, allowing us to identify the cases with the largest overall differences. These results are presented in the slide. We also defined the physical characteristic of input files. Based on the above data, no unconditional correlation can be established between file size or audio recording length and the success of authentication. For example, in the case of the analyzed recording, dataset 3 contains a longer audio clip with a larger file size, yet its similarity score is lower than that of dataset 1. To better understand these correlations, we proceed by calculating the average delta values for file size and audio length across the entire dataset, allowing us to access the overall differences. It appeared that dataset 3 has bigger average file size, preliminary 10 kilobytes greater, and almost the same length of audio record, but do not have false positive cases. These findings suggest that for short audio records within the length of 1.5 seconds, files with a content size exceeded 270 kilobytes are likely to produce voice prints suitable for reliable person authentication with a probability of 80%. In a previous scenario, we used voice print received from short audio records produced by the same person. Now we try to compare the audio records from different speakers in order to determine the rate of false positive cases under these conditions. We use the same data sets, 1 and 3, but now we compare each file from one dataset with each file from another dataset. The results obtained in this test are consistent with these expectations. No successful matches or false positive results were expected when comparing audio recording from different speakers. However, we still have 22% of threshold cases, which unacceptably big value for this scenario. In two previous scenarios, we used voice prints received from short audio records, and potentially it could affect the quality of voice prints due to the lack of data required for Resemblyzer voice print generator to analyze. To address this, we now examine a scenario in which one of the voice prints in each comparison pair is derived from a longer recording. Specifically, we use dataset 2. As you can see, it's a male voice with the length the length of audio is 15.78 seconds. And data set 4, it's a female voice with audio length 20.88 seconds. This experiment involves calculating similarity scores between voice prints from dataset 1 and voice prints from dataset 2, and likewise between voice prints from dataset 3 and voice prints from dataset 4. Result of comparison of dataset 1 with dataset 2 and dataset 3 with dataset 4 are illustrated in the slide. As you can see, in both cases, no successful matches were observed, with a high proportion of results falling into the threshold and false positive categories. These findings indicate that voice prints generated from short audio recordings of 1 to 1.5 seconds are not suitable for the reliable authentication when compared against a high-quality voice print. In the following experiment, we tried to increase the quality of input audio records by increasing the length of audio records and file size to approximately twice in comparison with the original dataset 1 and 3. Details of dataset 5 are provided in the table. As a first step, we repeat the initial experiment calculating similarity scores by comparing the voice prints from dataset 5 with one another. The results of this comparison are presented in the table. Um, the results were found to be very promising. Accordingly, no false positive cases were observed, and the proportion of threshold values is really minimal. Next, we repeat the experiment by comparing dataset 5 with the high-quality voice print obtained from dataset 2. The results of this comparison are presented in the slide. The obtained findings indicate strong performance, suggesting that audio records with a duration at least 2.63 seconds and file size of 495 kilobytes or greater can produce reliable voice prints suitable for secure user authentication. The present study has demonstrated in practice that the Resemblyzer library can be effectively employed on portable devices with limited hardware resources and no access to cloud services. The experiments confirm that the library delivers highly reliable results in voice authentication using relatively short audio recordings, no longer than 3 seconds, in duration and under 500 kilobytes in size, which aligns well with the typical timing of short voice commands. These findings highlight the potential of Resemblyzer for integration into autonomous resource-constrained systems and provide a foundation for further research into its applicability in more complex operational scenarios for independent portable devices. Thank you for your attention.